All across the immense reaches of time and space, energy is being exchanged, transferred, released. In a great cosmic pinball game we call our universe. How does energy stitch the cosmos together? And how do we fit within it? We now climb the power scales of the universe. From atoms, nearly frozen to stillness, to Earth's largest explosions. From stars, colliding, exploding, to distant realms so strange and violent, they challenge our imaginations. Where will we find the most powerful objects in the universe? Today, energy is very much on our minds as we search for ways to power our civilization and serve the needs of our citizens. But what is energy? Where does it come from? And where do we stand within the great power streams that shape time and space? Energy comes from a Greek word for activity or working. In physics, it's simply the property or the state of anything in our universe that allows it to do work. Whether it's thermal, kinetic, electromagnetic, chemical, or gravitational. The 19th century German scientist Hermann von Helmholtz found that all forms of energy are equivalent, that one form can be transformed into any other. The laws of physics say that in a closed system, such as our universe, energy is conserved. It may be converted, concentrated, or dissipated, but it's never lost. James Prescott Joule built an apparatus that demonstrated this principle. It had a weight that descended into water and caused a paddle to rotate. He showed that the gravitational energy lost by the weight is equivalent to heat gained by the water from friction with the paddle. That led to one of several basic energy yardsticks, called a joule. It's the amount needed to lift an apple weighing 100 grams 1 meter against the pull of Earth's gravity. In case you were wondering, it takes about 100 joules to send a tweet. So tweeted a tech from Twitter. The metabolism of an average-sized person going about their day generates about 100 joules a second, or 100 watts, the equivalent of a 100-watt light bulb. In vigorous exercise, the power output of the body goes up by a factor of 10, 1 order of magnitude, to around 1,000 joules per second, or 1,000 watts. In a series of leaps by additional factors of 10, we can explore the full energy spectrum of the universe. So far, the coldest place observed in nature is the Boomerang Nebula. Here, a dying star ejected its outer layers into space at 600,000 kilometers per hour. As the expanding clouds of gas became more diffuse, they cooled so dramatically that their molecules fell to just 1 degree above absolute zero, the total absence of heat. That's around 1 billion-trillionths of a joule. That makes the signal sent by the Galileo spacecraft as it flew around Jupiter seem positively hot. By the time it reached Earth, its radio signal was down to 10 billion billionths of a watt. Now jump all the way to 150 billionths of a watt. That's the amount of power entering the human eye from a pair of 50-watt car headlamps a kilometer away. Moving up a full 7 powers of 10, moonlight striking a human face adds up to 300 thousandths of a watt. That's roughly equivalent to a cricket's chirp. From there, it's a mere 5 powers of 10 to the low-wattage world of everyday human technologies. Put 10 100-watt bulbs together. At 1,000 joules per second, 1,000 watts, that roughly equals the energy of sunlight striking a square meter of Earth's surface at noon on a clear day. Gather 200 bulbs. 20,000 watts is the energy output of an automobile. A diesel locomotive, 5 million watts. An advanced jet fighter, 75 million watts. An aircraft carrier, almost 200 million watts. The most powerful human technologies today function in the range of 1 billion to 10 billion watts, including large hydroelectric or nuclear power plants. At the upper end of human technologies was the awesome first stage of a Saturn V rocket. In 5 separate engines, it consumed 15 tons of fuel per second to generate 190 billion watts of power. How much power can humanity marshal? And how much do we need? Long before the launch of the space age, visionaries began to imagine what it would take to advance into the community of galactic civilizations. In the 1960s, the Soviet scientist Nikolai Kardashev speculated that a level 1 civilization would acquire the technology needed to harness all the power available on a planet like Earth. According to one calculation, we are 0.16% of the way there. This is based on British Petroleum's estimate of total world oil consumption, some 11 billion tons in 2007. Humans today generate about 2.5 trillion watts of electrical power. How does that stack up to the power generated by planet Earth? Deep inside our planet, the radioactive decay of elements such as uranium and thorium generates 44 trillion watts of power. As this heat rises to the surface, it drives the movement of Earth's crustal plates and powers volcanoes. Remarkably, that's just a fraction of the energy released by a large hurricane in the form of rain. At the storm's peak, it can rise to 600 trillion watts. A hurricane draws upon solar heat collected in tropical oceans in the summer. You have to jump another power of 10 to reach the estimated total heat flowing through Earth's atmosphere and oceans from the equator to the poles. And another 2 to get the power received by the Earth from the Sun at 174 quadrillion watts. Believe it or not, there's one human technology that has exceeded this level. The AN-602 hydrogen bomb was detonated by the Soviet Union on October 30th, 1961. It unleashed some 1,400 times the combined power of the Nagasaki and Hiroshima bombs. With a blast yield of up to 57 million tons of TNT, it generated 5.3 trillion watts, if only for a tiny fraction of a second. That's 5.3 yottawatts, a term that will come in handy as we now begin to ascend the power scales of the universe. To Nikolai Kardashev, a level 2 civilization would achieve a constant energy output 80 times higher than the Russian superbomb. That's equivalent to the total luminosity of our Sun, a medium-sized star that emits 375 yottawatts. However, in the grand scheme of things, our Sun is but a cold spark in a hot universe. Look up into southern skies, and you'll see the Large Magellanic Cloud, a satellite galaxy of our Milky Way. Deep within is the brightest star yet discovered. R136A1 is 10 million times brighter than the Sun. Now, if that star happened to go supernova, at its peak, it would blast out photons with a luminosity of around 500 billion yottawatts. To advance to a level 3 civilization, you have to marshal the power of an entire galaxy. The Milky Way, with about 200 billion stars, has an estimated total luminosity of 3 trillion yottawatts. A 3 followed by 36 zeros. The author Isaac Asimov imagined a galaxy-scale civilization in his Foundation series. Galaxia, he called it, is a superorganism that surpasses time and space to draw upon all the matter and energy in a galaxy. But who's to say that's the upper limit for civilizations? To boldly go beyond level 3, a civilization would need to marshal the power of a quasar. A quasar is about 1,000 times brighter than our galaxy. Here is where cosmic power production enters a whole new realm, based on the physics of extreme gravity. It was Isaac Newton who first defined gravity as the force that pulls the apple down and holds the Earth in orbit around the Sun. Albert Einstein redefined it in his famous general theory of relativity. Gravity isn't simply the attraction of objects like stars and planets, he said, but a distortion of space and time, what he called spacetime. If space-time is like a fabric, gravity is the warping of this fabric by a massive object like a star. A planet orbits a star when it's caught in this warped space, like a ball spinning around a roulette wheel. Some scientists began to wonder, if matter became dense enough, could it warp space to such an extreme that nothing could escape its gravity, not even light? With so much power being emitted from such a small area, scientists suspected that quasars were actually being powered by black holes. How a totally dark object can do this has been narrowed by decades of observations and theory. If a black hole spins, it can turn into a violent cosmic tornado. Gas and stars begin to flow in along a rapidly rotating disk. The spinning motion of this so-called accretion disk generates magnetic fields that twist up and around. These fields can channel some of the inflowing matter out into a pair of high-energy beams, or jets. Gas and dust nearby catch the brunt of this energy, growing hot and bright enough to be seen billions of light years away. Amazingly, the power of a black hole can rise to even greater extremes at the moment of its birth. As a giant star ages, heavy elements like iron gradually build up in its core. As its gravity grows more intense, the star begins to shrink until it reaches a critical threshold. Its core literally collapses in on itself. That causes the star to explode in a supernova. And now, in death, the star can unleash gravity's true fury. In the violence of the star's death, gravity can cause its massive core to collapse to a point, forming a black hole. In some rare cases, the newborn monster powers a jet that accelerates to within a tiny fraction of the speed of light. For a few minutes, these so-called gamma-ray bursts are known to be the brightest events since the Big Bang. 3 orders of magnitude above a quasar, at a billion yottawatts, a 10 with 42 zeros. Remarkably, they are still not the most powerful events known. Albert Einstein's equations contained an astonishing prediction: that when massive bodies accelerate or whip around each other, they can stir up the normally smooth fabric of space-time. They produce a series of waves that move outward, like ripples on a pond. Scientists are now hoping to detect these gravitational waves and verify Einstein's prediction using precision lasers and some of the most perfect large-scale vacuums ever created. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they are hoping to record the collision of ultra-dense remnants of dead stars known as neutron stars and of black holes. According to computer simulations, as two black holes spiral into a fateful embrace, the energy carried by each gravity wave rises 5 orders of magnitude above a gamma-ray burst, to 100 billion trillion times the power of our Sun. Does the collision of black holes define the known power limits of our universe? Perhaps not. As turbulent as the environment of a black hole might be, its true power may well lie deep in its core. A black hole's mass is enshrouded within a dark sphere called the event horizon. Since the 1920s, scientists have described the mathematics of the event horizon as the equivalent of a waterfall. It's the point of no return, beyond which water falls freely into the gorge. At the event horizon of a black hole, space itself falls freely in at the speed of light. If the black hole is spinning, then the flow spirals down and around an inner horizon that envelops the singularity. That's the central region where space-time becomes infinitely warped. Any matter that rides this river of space whips around the inner horizon so fast that centrifugal force tends to fling it back out. As that happens, it collides with matter that's streaming in, whipping up a ferocious cosmic storm. The energy of the colliding stream feeds upon itself, rising to what may well be a limit imposed by nature. It dissipates only as it falls into the singularity and disappears. Fortunately for us, gravity walls off such energy extremes behind the event horizon, where they cannot affect the rest of the universe. And so here we sit. Our world is nestled within a vast stream of cosmic energy, somewhere between the spin of an electron and the maelstrom of a black hole. There's no telling whether a future Earth civilization will be able to harness enough energy to advance into the cosmos. For now, as we tap into the tiny morsels of power at our disposal, we venture a closer look at a universe blazing with activity. We are its product, and its starstruck admirer.
From the chaos on the outer planets to the broiling heat of Earth's closest neighbor, radical weather is the norm in the solar system. We do have our own extremes here on Earth, but they pale in comparison to the fastest, dustiest, wettest, and most brutal alien storms. On Earth, the sun drives our weather, and sometimes drives it wild. When hot and cold collide in the atmosphere, watch out. This is true locally and globally. But storms on other planets are bigger, badder, and stranger than their counterparts on Earth. Why is that? Because of the sun? If not, what else fuels their fury? The basic laws of nature, the rules of the game, are pretty much the same wherever you go in the solar system. But every planet has its own way of playing the game. Right now on Mars, the entire planet is being covered in dust. This global dust storm blocks 99% of the sun's rays from reaching the planet's surface. It's actually a system of smaller but still massive storms churning dust high into the atmosphere. Once it starts, it takes months for Martian skies to clear.
Mars is just the most dramatic weather in the solar system in some senses. It's very rare in the solar system you get a weather event that can take out the whole planet.
So if the basic rules of hot and cold are the same on Mars, why is the weather so different from Earth? For one thing, Mars is half the size of Earth. It's also 50% further from the sun, so it's much colder. The average temperature on Mars is minus 80 degrees. That's almost 130 degrees colder than Earth. And the atmosphere is extremely thin and composed mostly of carbon dioxide. But perhaps the most important difference is this: Mars is a global desert.
What would Earth be like without water? Well, you'd probably have a lot of dust. There's no liquid water at the surface of Mars, and there's very little water in the atmosphere, and so there's nothing to sort of keep the dust down.
On Earth, dust storms are localized and short-lived.
The reason for that difference in scale is that the storms are generating their own weather on Mars, whereas on the Earth, they're slave to the weather that's going on around them.
In other words, on Earth, the global weather system creates dust storms. On Mars, the storms create a global weather system. Astronomers have always been able to see big Martian dust storms easily with Earth-based telescopes. But what they couldn't see was what caused them. That would require a trip to Mars itself. In 2003, NASA landed 2 rovers called Spirit and Opportunity on the Martian surface. Their mission? To learn more about the geology of the red planet. NASA engineers always assumed that as these 2 vehicles roamed the Martian surface, dust would build up on their solar panels.
If you have a lot of dust that's falling down out of the atmosphere and coating the panels, pretty soon you're not getting much sun to the silicon. And in fact, we thought that was what was going to kill the rover Spirit and Opportunity.
Only it never happened. The rovers didn't die as expected. As dust built up on the panels, somehow something would clean them off. But how could this be? NASA engineers were baffled until the rovers themselves saw the culprit. Martian dust devils.
It turns out that dust devils were sort of our white knight. They came along and cleaned off the solar panels just at the time we were expecting to start having some problems.
There are beautiful photos that actually show dust devils moving across the Martian atmosphere and ghostly soldiers moving out there in the distance.
A dust devil is really an extreme form of rising hot air, or convection.
And that hot air wants to go up, and it comes up just like, water going down a drain. Well, this is air that just spirals up into the colder parts of the atmosphere.
Whenever warmer air, which is less dense, rises up through cooler air, which is more dense, it rotates as it swirls upwards. Convection can be very powerful, strong enough to lift things up. On Earth, it lifts moisture, and that's how thunderstorms form. But on Mars, there is no moisture, so it lifts dry, dark dust and creates giant dust storms instead. Once airborne, Martian dust clouds absorb sunlight and heat the atmosphere. This supercharges the convection, lifting still more dust.
That produces more winds, which bring up more dust, and these things can spread up to thousands of miles across, or even, in some cases, they can envelop the entire planet.
And because the Martian atmosphere is so thin, it doesn't take much to get this cycle going.
You get a lot more difference between the surface temperature and the air temperature, and so the convection on Mars is very much more vigorous.
As a rule, Earth doesn't get the temperature extremes that Mars does. But sometimes, here and there in the deserts of Earth, convection can be very Martian-like. And we get dust devils, too. But at Arizona State University, Lynn Necrace makes dust devils to order in a lab to study them up close. He uses a vortex generator and substitutes lighter, dry ice for dust. What he creates is not an exact replica of how real dust devils form, but good enough to see how they pick up dust and debris.
Natural dust devils usually form from the bottom up, as opposed to tornadoes, which form from top down. So what happens when we turn this on, we have the airflow starting, and as the airflow starts to rotate from the fans down to the floor, we actually end up having the vortex form.
In other words, the vortex generator, basically a huge vacuum cleaner, imitates the swirling action of convection.
You can see here there's a wider base where larger particles of the dry ice are being swept up and gets wrapped up and tightens as it expands upward. The center of the core is where the majority of the lifting would occur.
Martian dust devils have been helpful, keeping the rovers clean. But could they actually be making a mess of the rest of the planet? Some scientists think there are so many at any one time, and they lift so much dust into the atmosphere, that together they trigger these much larger dust storms.
It starts wind patterns, and the air's warmer over here, and it's colder over here, and the air starts moving around. Pretty soon you're spreading dust over the whole planet.
And we found measurements that indicate there's up to maybe 200 dust devils per square mile per day during some parts of the summer.
And they can range from a couple of 100 feet tall to devils that stretch 6 or 7 miles high.
You can get just towering monsters of dust devils that we would never see on the Earth. The kind of maximum-sized dust devils you see on Mars are more like tornadoes on the Earth, where they're going up almost 10 kilometers. So these things are just real monster systems.
Back at Arizona State University, scientists blow crushed walnut shells as silicate particles in the Planetary Geology Wind Tunnel to replicate dust and wind conditions on Mars.
If we can understand and sort of replicate what's going on, then we can, in a sense, understand how the Martian surface has been changing and continues to change as time goes on.
Oddly enough, their studies reveal that it's easier for winds to loft larger sand particles into the air than smaller dust particles.
This is because there's cohesional forces and static forces between the very small, fine dust grains. We imaged the rover deck and actually found that sand seemed to have bounced onto the solar panels, and we can see the skip marks across the surface. And this is interesting because we don't usually see sand typically reach that high.
Dust devils on Earth never have the punch to produce that kind of chaos here. Lucky for us. But what would happen to Earth if a giant Martian-style dust storm did overtake us?
If you had dust storms of Martian size on the Earth, you would find your city being enveloped in an orange-tan haze.
Air quality plunges as the storm churns. Dust blots out the sun, shutting down photosynthesis. No plants, no food. Temperatures would plummet. 65 million years ago, an asteroid may have struck the Earth, creating these same conditions, wiping out the dinosaurs.
It's not going to happen on the Earth, though, because there's going to be rainfall and moisture condensing on the dust grains and so forth and dropping them out of the atmosphere. So it's very hard for something like that to spread in the climate conditions that we have on Earth.
Forecasting Martian weather may someday be just as important as forecasting the weather on Earth. If we ever want to send a manned mission there,
The word environment no longer really applies just to the meadow next door and the little stream down at the end of town. It's the whole inner solar system. I mean, that's really our environment now.
the sun's energy bathes all the planets. On Earth, it creates hurricanes. On Mars, planet-wide dust storms. But with almost no solar energy, distant Neptune produces violent and powerful winds. Where do they come from? And just how bad are they? If Neptune's winds were to travel to Earth, these alien storms would literally blow us away. The orbit of Neptune lies 3 billion miles from the Sun, at the outer edge of the solar system. There's a lot we don't know about this big blue planet. Neptune's jet stream winds blast as fast as 1,500 miles an hour in its upper atmosphere. But how? The sun controls the weather on Earth and Mars, but it barely reaches out here. No sunlight means freezing temperatures, an average of minus 392 degrees Fahrenheit. So if there's no sun and no heat, where do these incredible winds come from?
One of the interesting puzzles is that as you go further out in the solar system, you get further from the sun, the winds don't go down. You still get very strong winds.
The energy for Neptune's winds must come from somewhere, and scientists are working to figure it out.
Neptune's energy is certainly not going to be powered by solar radiation. In fact, the energy we detect coming out from the planet in the infrared as heat is 2.5 times the energy coming in from the sun.
So the planet is creating its own heat, not from its core, which is made of rock and ice, but wrapped around this icy center is a mantle of ammonia, methane, and water, all being squeezed by enormous pressure and generating tons of heat. So while Neptune is frigid on the outside, on the inside it's giving off a lot of heat. This heat may help generate Neptune's winds, but they're still too strong to come from the mantle alone. Something else is pushing them faster and faster. Earth has a hot core too, and it's a lot closer to the sun. So why don't we have winds like Neptune? For one thing, our oceans store and release energy, and that helps generate our weather.
That adds energy in places, takes it out in others, in a very complicated system.
This complicated system produces a lot of wind. And just where are Earth's fastest winds found? Surprisingly, not over the ocean. They blow instead over the top of a fairly modestly sized mountain. New Hampshire's Mount Washington.
The highest winds ever observed by human beings were right here on Mount Washington at 231 miles an hour on April 12th in 1934.
Mount Washington Observatory, a private, non-profit scientific institution, is responsible for tracking the weather and climate atop the 6,288-foot tall mountain. This remote weather station, accessible only by snow tractor in the winter, has kept daily records for the last 76 years.
It's definitely one of the most extreme locations on the planet. We regularly see in the wintertime winds exceeding 100 miles per hour every few days.
Nowhere near as ferocious as Neptune, yet still pretty strong. But why does this mountain, 1/5 the size of Everest, produce such fierce gusts?
We're at a place where we have winds converging from various directions, coming from the Ohio River Valley, coming down from the St. Lawrence River Valley, coming up the eastern seaboard, all converging here in this area on top of Mount Washington.
The elevation change from the valley floor to the summit of Mount Washington is very significant for any mountain range. It's over 4,000 feet, so air is forced to go over the mountaintop and forced to squeeze in there, and is accelerated as it's squeezed over the mountaintop.
And they measure it every hour, on the hour, 24 hours a day, 7 days a week.
It's blowing over 100 out here right now. Ice is forming on the instruments more quickly. It's time to go up and de-ice the instruments, even though it's blowing over 100. We gotta do it every hour now.
Ironically, Earth's uneven surface, which channels winds into powerful gusts on Mount Washington, ultimately knocks them down over time. And this is the big difference between weather on Earth and weather on Neptune. Earth has mountains that slow winds down. Neptune is as smooth as a cue ball.
It's not so much a question of you're driving them stronger, because you're not. It's just that there's nothing to slow them down.
Simply put, once Neptune's winds get blowing, there's nothing to get in their way. So what would an average Neptune wind speed of 850 miles an hour do to us here on Earth?
We have parking level winds in the Earth sometimes above 100 miles an hour. We consider that pretty dangerous. So if we sat with 900 mile an hour winds from Neptune on the Earth, we would probably start wiping out everything on the surface and scraping everything off.
Giant Neptune takes wind and transforms it into something extreme and almost unrecognizable. But orbiting just beyond the rings of Saturn is a small moon that does the same thing to rain. This is Titan, where an everyday rain shower would turn Earth into an explosive fireball. It's a cloudy day, and a gentle rainstorm starts. Here on Earth, you'd grab your umbrella and consider it a minor inconvenience. But this isn't Earth, and it's no ordinary rain. You're on Titan, a small moon of Saturn. And in this chemical downpour, you'd need more than an umbrella to protect you. The rules of Earth weather definitely don't apply here. But Earth and Titan are alike in a lot of ways. On Earth, we have a solid surface, a protective atmosphere, and plenty of water. All these things make life on our planet possible. There's really nowhere else quite like Earth anywhere in the solar system. But Titan comes close. Like Earth, it has a solid surface, and that's not all.
Titan has an atmosphere that's, in general, very similar to Earth's. In some ways, it's mainly nitrogen, like Earth's atmosphere. It's rich with organic material, also like Earth's atmosphere.
But similar isn't the same. Here on Earth, our atmosphere has a huge supply of water in it all the time, constantly evaporating and raining back down, like here on the Hawaiian island of Kauai.
Today we're on the slopes of Mount Waialeale, which is the cloud-shrouded mountain behind us. It rains over 40 feet a year here.
Earth's water cycle starts when warm, moist ocean air rises, forming clouds that eventually condense into rain. The rain falls back onto the land, where it eventually drains back into the ocean, starting the cycle again.
When water evaporates, it absorbs solar radiation. When water condenses, it releases all that energy into the atmosphere. And this transfer of heat helps to moderate conditions on Earth.
Earth's water stores as much as 80% of the sun's heat, helping keep our temperatures steady from the equator to the poles. Scientists theorize that Titan might have water or some other liquid that might produce a similar effect. And in 2004, when NASA's Cassini probe visited Saturn, it found some pretty good evidence to support that idea.
If you went to Titan and you were looking at the landscape, you would see something that in some ways would look almost familiar to you. You might see big mountains and valleys that were carved out by running liquids.
In fact, as Cassini flew past hazy Titan, its radar read the surface below. Scientists saw channels cutting across the surface, much like rivers on Earth do, some as long as 900 miles. The first strong evidence of liquid on Titan.
There are large bodies of liquid on the surface of Titan. Nowhere else in the solar system except for the Earth are there any large bodies of liquid.
Could water, the liquid that carves Earth's mountains and valleys, also be carving these features on Titan's surface? Or could it be something else? The problem is that Titan is too far away from the sun. If it was water, it would be frozen solid.
It's about minus 300 Fahrenheit on Titan, so things behave very differently on Titan than on Earth. Because it's so cold, methane, which is a gas on Earth, is a liquid on Titan.
One mystery solved. But just because methane is a liquid on Titan's surface doesn't mean it's part of a weather cycle like water on Earth. So how do we know that this methane also falls from Titan's sky? That answer is shrouded in mystery, literally.
Titan's completely covered in a thick haze of smog particles, like a very, very bad day in Los Angeles.
Despite the haze, the Cassini probe once again revealed the answer.
We can see the upper clouds, and we can see evidence for rainfall because the clouds drop very precipitously. We hypothesize that we're seeing the effects of rainfall.
Methane rainfall.
We think that Titan has methane monsoons, so we think that sometimes Titan has a lot of rain that is able to carve rivers and leave large fluvial deposits on the surface.
Cassini's radar imaging also revealed large methane seas on Titan's surface.
If you have liquid methane on the surface, in a lake, for example, that methane can evaporate off and become methane gas in the atmosphere. So you have kind of a cycling of methane between liquid phase and gaseous phase and between the surface and the atmosphere. That's very similar to the water cycle that occurs on the Earth.
But methane is a flammable gas. So why isn't Titan on fire?
For any combustion, you need two things. You need both a fuel, which methane is, but you also need oxygen. And on Titan, you lack the oxygen. So the whole thing is basically a big fuel canister, but there's no oxygen with which to burn it, and so it's all very stable.
If it were cold enough here on Earth to produce methane rain, the oxygen in our atmosphere would create a worldwide firestorm. Luckily for us, that can't happen. Titan's methane cycle makes it both alien and familiar to us.
To me, Titan is very exciting because all the materials are so different, and yet these processes produce very similar landscapes to what we see on Earth.
Titan proves that where alien weather is concerned, looks can be deceiving. On Jupiter, it's all about size. Drop the Great Red Spot onto our world, and it makes even our worst hurricanes look like a breeze. This is the biggest and oldest storm in the solar system, and Jupiter's most famous feature. It even has its own name, the Great Red Spot.
It's about 2 or 3 times the size of the Earth, which makes it the mother of all storms.
We've known about the Great Red Spot in Jupiter's southern hemisphere for more than 300 years.
When Galileo invented the telescope, within a few tens of years, people had seen the Great Red Spot, and it's still there.
Familiar yet mysterious. Nobody knows how the Great Red Spot formed. But scientists are finally probing below Jupiter's cloud tops to uncover more about this enormous alien storm. The storm is powerful. With wind speeds of 300 miles per hour, it rises miles above the surrounding clouds. On Earth, we have storms that seem similar, though smaller and milder. Hurricanes, also known as cyclones or typhoons, depending on where they form. They're our most destructive weather systems. But is there more than just a passing resemblance between Earth's cyclones and Jupiter's red spot?
When you look at the Earth from space at a hurricane, it's this big swirling pattern. It's round, it rotates. Jupiter's big storms look big and round and cloudy, and they rotate. But there the similarity ends.
In a hurricane, there is an internal core, which is called the eye of the tropical cyclone. And that's a region of very calm winds and no clouds. And usually has a size of about 10, 20 kilometers in diameter. And then away from the eye, there is the eye wall. Those are really cloudy regions with a lot of rain. And as you move outward, there is a whole region of about a couple of 100 kilometers with very, very strong winds and very strong rain.
Hurricanes draw power from heat in our oceans. But Jupiter has no oceans. And the sun isn't close enough to power a storm as big as the Great Red Spot. So where does it get its strength? Part of the answer is Jupiter's size. It's the largest planet in the solar system, almost as big as all the other planets combined. This mass generates a very strong gravitational pull, which in turn creates interior heat that rises to the surface. Another piece of the puzzle may be Jupiter's hypersonic rotation. Despite being much larger than Earth, Jupiter's day lasts only 10 hours. In other words, it spins incredibly fast. Could energy from this dizzying spin feed the Great Red Spot?
The weather is really dominated by this fast spin. There's shearing between different latitudes, and that shearing, plus a lot of heat that comes up from the interior of this very massive object, 290 times the mass of the Earth, leads to very violent storms.
Both Jupiter's and Earth's storms spin around in a familiar spiral shape. On Earth, it's because of an effect called the Coriolis force.
I'm sitting at the North Pole, and I want to throw a ball down to a friend who's in Los Angeles. And so if I threw the ball in that direction, the Earth rotates, and the ball will end up in the middle of the Pacific rather than in Los Angeles. So it's like if the trajectory was deflected to its right. And that's what we call the Coriolis force.
This force spins storms clockwise in our southern hemisphere. But there is a stark difference between Earth and Jupiter. The Great Red Spot is in Jupiter's southern hemisphere, and yet it spins counterclockwise. This is because of some other powerful winds.
It's bounded by jets, which are moving in opposite directions. And so like a cog between two conveyor belts, they're just feeding energy and momentum into the system.
Jupiter's complex jet streams spin the storm into organized chaos. But the greatest difference between Jupiter's red spot and our storms may be Earth's solid surface. Once a hurricane hits land, it comes apart pretty fast.
Where they come over land or over mountains, their behavior is very different from where they form over the oceans, and over warm oceans in particular, where we get hurricanes. And on Jupiter, there's obviously no solid surface.
With no land mass to stop it, the Great Red Spot just keeps on spinning and spinning and spinning. Scientists hope to learn more about our weather by continuing to study the storm.
On Earth, there's a limit to how far ahead you can predict the weather. On Jupiter, we can forecast where the red spot is going to be months in advance. It's practical value to understand what makes weather on Earth so unpredictable, and aspects of the weather on Jupiter are much more predictable.
Unpredictable or not, Earth's weather never gets as violent as on Jupiter. That's lucky for us, because if we shrank the Great Red Spot down to fit on Earth, we'd be in for disaster.
On the Earth, we go up to Category 5 hurricanes, let's think about Category 10 hurricane here. Not much would be left.
Alien storms are vastly different everywhere you go in our solar system. Even our next-door neighbor, Venus. They say we're sister planets. Lucky the resemblance doesn't include weather. Otherwise, we'd get seriously burned. Venus may be our nearest neighbor, but somehow its weather is radically different from ours. The second planet from the Sun is a cross between a toxic waste dump and Death Valley, but even worse.
So it's almost a planetary definition of hell.
The temperature is 900 degrees Fahrenheit. The pressure on the surface is the same as half a mile below the Earth's ocean. And if that's not enough, the upper atmosphere of Venus is choked with sulfuric acid clouds and winds clocked at 250 miles an hour.
To get a comparison for Venus, the best thing to do is climb inside of your oven and crank it up. And then in terms of pressure, you're talking about deep sea diving. It's like nothing. There's nothing comparable on the Earth. It's just a very, very extreme object.
On Venus, there's just no escaping the heat.
If you built up a hot spot on Venus, the massive atmosphere would just carry that heat away and spread it around.
But Venus shines so brightly in the night sky because its thick clouds reflect almost all the sunlight it receives. In fact, some early scientists assumed Venus would have moderate Earth-like temperatures.
When we went by Venus in 1962 with a spacecraft, we thought we would find a surface at 90 degrees Fahrenheit, sort of like Miami, Florida.
We were dead wrong. Something else must be at work on Venus. But what? So why doesn't Venus cool off the same way Earth does?
On the Earth, for example, we have sunlight coming in, hitting the surface of the Earth. Earth warms up a little bit, but the oxygen and the nitrogen in the atmosphere don't impede the light, so when it gets released out in the infrared, it goes right through the atmosphere and leaves and goes into space.
But on Venus, the atmosphere is 97% carbon dioxide. giving a whole new meaning to the greenhouse effect.
It becomes very, very hard for the surface to get its energy out.
So Venus really taught us a lesson, that if you have a blanketing gas, a greenhouse gas, it can warm up the atmosphere tremendously.
But why does Venus have so much more CO2 in its atmosphere than Earth? The two have much in common. They're even called sister planets. They're almost the same size, have roughly the same amount of carbon, and billions of years ago, both had lots of water. But eons ago, their paths mysteriously diverged. On Earth, water fostered life.
The Earth has most of its carbon in life forms, in the trees and the animals. But if you took all that carbon that's in the near-surface rocks and burned it up or released it, you would then create an atmosphere very much like Venus.
Venus's close proximity to the sun made it too hot to sustain liquid water. Instead, its water evaporated into the atmosphere, trapping the heat deposited by the sun and creating a runaway greenhouse effect. Once in the atmosphere, the water molecules were exposed to solar ultraviolet rays that broke the molecules apart.
It really wasn't recognized by the scientific community how important the greenhouse effect was prior to going by Venus and seeing this amazing place where it was 900 degrees Fahrenheit, not 90.
It took several doomed missions to Venus to figure it out. Starting in the 1960s, both the United States and the Soviet Union sent unmanned probes past the planet and down to its surface. It didn't take long before Venus crushed and burned them. Then, in 1981, the Soviet lander Venera 13 set a record for survival on the surface of Venus. 2 hours and 7 minutes. It was able to take pictures and samples of the surface before being overcome by the heat.
You're sitting there with this 900 degrees Fahrenheit heat all around you. It's going to get in there and bake you after a while.
Scientists one day hope to send a probe to Venus that can survive its hellish environment, to help us confirm our theory of how this planet went astray. Because if circumstances were just a little different, our sister planet might just be our twin. Remove our atmospheric shield, and you're on the road to hell.
As soon as you're heated up to something like 400 degrees or so, you probably start getting some smoldering smoke, and way before it hit the 900 degrees, the Earth would burst into flames because of all the oxygen around.
Once the oceans boiled away, the carbon locked in rocks on the ocean floor would cook, and over millions of years re-enter the atmosphere.
Probably if you came back to the Earth system after this happened, you'd find a planet looking much like Venus.
We're a long ways away from such a drastic change, but it's sobering to look at Earth's sister planet when the sister planet went on a very different track than we did.
So cosmic forces turned Venus into a planetary barbecue. But on this violent, stormy world, time and the elements have produced some of the strongest thunderstorms ever measured. Welcome to Saturn. Lightning cuts the sky. This violent weather system grows bigger than the entire United States as it pummels the atmosphere with the most powerful lightning ever seen. Except this lightning can't be seen, because these bolts are electrifying the skies over Saturn. Despite the raw power of Saturn's lightning, scientists have been unable to see it, partly because Saturn's rings are too bright.
The rings are so bright, if you were on the night side of Saturn, it would be considerably brighter than the Earth under a full moon.
But Saturn also hides its lightning within thick, choking clouds of ammonia.
It's probably 100 kilometers down that the lightning is happening, and that complicates seeing the lightning flashes.
But the lightning is there, and scientists know it because they've heard it. Radio wave detectors on the Cassini orbiter have recorded the sound of Saturn's lightning.
We can hear the static of lightning just as you could with an AM radio going down the highway on Earth.
And this static reveals the power of the lightning that we can't see.
You can measure the energy in those radio waves and compare it with the energy that your radio picks up when there's a thunderstorm around on Earth. And the Saturn ones are big. They're more powerful, maybe 100 times.
And Earth's lightning can help scientists understand how storms work on Saturn. Within Earth's storm clouds, just like in Saturn's, updrafts drive moisture higher, causing ice to form. These ice crystals rub against each other, take on a positive charge, and become attracted to negatively charged water droplets lower in the cloud. This sets the stage for a potentially powerful discharge of energy.
Once you get that charge separation that builds up so intensely that some theorize that it can be as strong as 100 million volts, that the cloud then must release that energy.
On Saturn, the same thing happens on a much larger scale. In fact, the lightning is 100 times stronger than Earth's. That's a staggering 10 billion volts of electricity. Thunderstorms in Saturn's southern hemisphere span thousands of miles and can last as long as a month. But scientists aren't sure what makes Saturn's storms bigger and longer lasting. It could be Saturn's supersaturated atmosphere.
Probably the fact that there's more water in the atmosphere, pound for pound, on Saturn makes the storms bigger.
More water droplets means more friction, which means bigger lightning bolts. But energy emerging from the planet may also contribute to the power in Saturn's thunderstorms.
It turns out that where Lightning Alley is on Saturn is a place where the winds are flowing the slowest. If you go deep down in the atmosphere, you'll see the same winds as you do up high. It's a place where the energy being released deep down below can make it on up to the upper atmosphere without being sheared apart, and allows storm systems to be organized.
Earth's atmosphere isn't built that way. So, as violent as our storms get, they're nothing compared to the systems on Saturn. Even a run-of-the-mill mega thunderstorm on Saturn would devastate us here.
A Saturn-sized thunderstorm on the Earth would mean a thunderstorm that grows to cover all of North America and presumably has very strong winds and rain. This is something that's unprecedented on the Earth.
Saturn's hyper-violent thunderstorms are proof that our planetary neighbors have weather far more ferocious than ours. But the laws of physics that create Saturn's storms are the same laws that create our own weather. Massive dust storms, unrelenting winds, killer lightning, powerful hurricanes, and searing heat.
Time is flying by on this busy, crowded planet. As life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth, at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. it may be a blip within a much grander sweep of time. When, we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons, birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras, and its ancient creatures? And where did our world come from? How and when will it end? In the revolutions spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow. Entropy, based on the second law of thermodynamics, holds that states of disorder tend to increase. From neat, orderly starting points, the elements, living things, the Earth, the Sun, the galaxy, are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy, in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow? Or will time stubbornly keep moving forward? We are observers and pawns in this cosmic conflict. We seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe, from the mechanical clocks of old to the decay of radioactive elements, or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, if you're judging by the stars, not the sun. Earth got its spin at the time of its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing it to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days, and why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by our retinas, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Our days and our lives are short in cosmic terms, but with our minds, we have learned to follow time's trail out to longer and longer intervals. 0.256. We know from precise measurements that the Earth goes around the solar energy that hits our planet is reflected back to space or absorbed by dust and clouds. The rest sets our planet in motion. You can see it in the annual melting and refreezing of ice at the poles, in the ebb and flow of heat in the tropical oceans, or seasonal cycles of chlorophyll production in plants on land and at sea. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time, as the Earth rotates on its axis, it makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. It can take a volcanic explosion or a dramatic lowering of sea levels to release this carbon back into the air, often after millions of years. The processes that shape a planet like ours play only the smallest of roles in the evolution of the universe. So to glimpse time's broader arcs, we must look to cycles that govern the larger cosmos. The reigning theory is that the universe began in a sudden expansion of space, the Big Bang. With entropy uniformly low, this was the time of the tiny. Subatomic particles like quarks and leptons stirred into a hot soup. They combined into atoms, setting in motion the primordial era. The universe cooled as it ballooned, growing dim and falling into what's known as the cosmic dark ages. After several 100 million years, larger clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. This glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. Trillions upon trillions of stars lit up galaxies all across the cosmos. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite to form generations of smaller stars, like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. In time, solar winds push their outer layers so far out, they blossom in spectacular displays. That's just what happened about 12,000 years ago to the star that spawned the famed Helix Nebula. On the inside, spokes of denser gas stubbornly resist the star's relentless winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of Earth, but about 200,000 times more dense. This is likely what's in store for our sun. A distant civilization may scan it for planets, and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars, and stars burning themselves out on a variety of timescales. In time, though, as the mass of the galaxy collects in successive generations of small stars, it will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way. At just about the time our sun begins to swallow our planet, any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new, larger galaxy. Dust-ups like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. You can see evidence of this now, out in the huge voids of space between filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break. The distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues to how they got there. At more distant reaches of time, tens of billions of years from now, the sky will grow darker and darker as everything recedes away from everything else. A good place to be in those long twilight years of the stellar era is a place where gravity and energy have forged an extended truce. Perhaps a place like this. Not much larger than our planet Jupiter, a red dwarf is one of the smallest and dimmest stars in our universe. They have been shown to harbor planets close enough that their dim rays can sustain liquid water and life. Brown dwarfs and red dwarfs form the vast majority of stars in our galaxy. In fact, combined, their mass exceeds that of all the large stars. Because they burn so slowly, they'll be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as their host galaxies grow dim, another process will begin to transform these small outposts. Over time, chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling, and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era. Around a billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal: to define the final time horizons of our universe, as well as the final moments of its most persistent objects. Black holes, ranging from millions to tens of billions of times the mass of our Sun, occupy the centers of large galaxies today. As those galaxies age, over trillions of years of time, much of their mass will spiral toward the center and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other. But when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. That has the effect of slowly siphoning energy and mass from the whole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider can pack. That is, unless there's more to nature and to gravity than we've thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the 3 spatial dimensions, plus time that we experience in our everyday lives. We may be like an insect living on the two-dimensional surface of a pond, unaware of the deep and complex reality below it. It may be possible that an unseen extra dimension could intersect our world on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro black hole could come from the extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. Its presence will open a brief window to a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when the clock strikes 10 to the 100th years from now, a number known as a googol. That's the end of the universe as we know it. But look beyond that to say 10 to the googol, a googolplex years. If you wrote all the zeros in that number in tiny one-point font, it would stretch beyond the observable universe. Will the great arrow of time have come to rest by then? Not if modern theories are correct. They hold that our universe is part of a much larger cosmic cycle of birth and death, with whole new universes coming into being in the space beyond our own. The time horizons of our universe may well be a blip in this grander scheme of things. Back to Earth now. We are products of the great era of stars and witnesses to its great spectacles of gravity and energy. No doubt there are other beings somewhere out there who are attempting to comprehend the universe. They too may invent the idea of time and develop their own theories on where it's all leading. Their discoveries and ours will not survive the entropy at work in the universe, as we all go the way of the stars, and as our universe gives way to grand new eras in the life of the cosmos.